Sure, I got your message. Please go ahead. I was just going to ask if you're ready to go, so that answers that. Um, and welcome to everybody. Hope you all having a good day as we socially distance here. Um, I'm Roger, and today we're going to talk about battery backup photovoltaic systems. um, I'm a retired university guy who then, after retiring, went out, worked in the field in solar. And today we're going to talk about battery backup systems because we gave an introductory to solar program a while back, and folks came back and said, well, can you tell us anything about battery backup systems? And I was thrilled because I cut my teeth on them about 15, actually 20 years ago. So let's talk about battery backup photovoltaic systems. I'm going to take maybe a slightly different approach because my feeling, things are going so fast right now. You see in front of you there the Tesla Powerwall system. Things are going so fast that my contention is that if one wants to stay up with what's going on, they have to understand what's inside the boxes and why they work the way they work. So we're going to do that first. We are going to do some very basic stuff and some very basic systems the way they were designed with components 15 years ago. And then we're going to take a look at how folks have improved that process significantly since then, and why people are going after these things like there's no tomorrow, or like they won't have electricity tomorrow, or whatever the reason might be. Okay, so let's move on here, and let's first talk about a couple of things that we have. Battery backup photovoltaic system. We are not talking about off-grid systems here. We're talking about systems that are tied into the utility. And but every once in a while, those utilities, they go down. There's an ice storm or a hurricane or something. You lose power for an hour, a day, or a week, whatever the case may be. And a lot of folks, I know up on Long Island, there was a lot of concern over nasty storms this winter. And I know that quite a few natural gas generators went in, and I think a few solar backup systems went in. Here in Florida, we've got lots of battery backup systems in place. And so let's take a look at what they look like, and then we'll see what's inside the box. Here's just a basic one-line diagram of how a whole house backup system might work. The key is that set of normally closed contacts you see in the middle. Let's see, I wonder if maybe you can even see my cursor if I point at it. I'm going to point at it, and I'm also going to say where I'm pointing. And this system, this is the fancy control box here. And when utility is lost, those contacts open and disconnect the structure. Let's call it a residential or house, whatever, but this can be larger scale as well. Most of these systems are scalable up to close to 100,000 watts. So we'll be talking in the 10,000 watt range today, but it's possible to do better than that. So in any case, once those contacts break, then there's no electricity left unless we have an IEEE 1547 compliant renewable energy source available, which would then generate electricity for the loads in that panel. And at night, if this compliant source happens to be solar, when there's no sun, then the energy storage system has to take over and supply the energy at night. And the whole idea here is you need to disconnect from the utility if the utility goes down, because the people trying to fix it don't appreciate if somebody's solar system is dumping an extra 7,600 volts onto one of the lines in the street if they're trying to fix it. So that's IEEE 1547 for small systems, got to disconnect so the utility can work on getting the power back up. So this would be a whole house backup system, and that could be requiring an awful lot of energy storage, because if you have a large house, it's not unusual to use maybe 50 kilowatt hours a day, and that means storing a lot of energy. In a partial house backup, maybe then there's a few loads you're willing to forego in order to make sure that you can make coffee in the morning and have a microwave oven and run your computer and a few lights and a few other things. And that system would look like this, where you have your main distribution panel that has interruptible loads in it. And then you have the fancy control box, which everybody who makes one of these has a different name for it, whether it be Enphase or Powerwall, Tesla, and several others. So here we allow some of the big loads to be interrupted. Maybe that's that 5-ton air conditioner, and shut off at a sub feed from that interruptible load panel, which feeds an uninterruptible load panel of relatively smaller loads. And then we do the same thing, make the energy storage and the solar available to the standby smaller uninterruptible loads, which might be more on the order of 10 to 20 kilowatt hours a day. It's all a matter of how many batteries you want to pay for and how much room you have on your roof for solar to make sure those batteries stay charged. So we're going to take a look at what it takes to make these things happen. If we're going to look at a few National Electrical Code issues, and here connecting to the utility, all those rules are in the National Electrical Codes, Chapter 705. 705.12b to more specific, to connect on the load side of the main. So bottom line is you have to have the right kind of inverter to make these things happen. And I'm going to, if you're really interested in this stuff, there is an appendix that we will not have time to go through today, that if you decide you want to go through the appendix, you can order a set of slides when you do the thing about getting your certificates and so forth. And Mr. PDH has a brand new PDF copy of this presentation that he will be happy to send to you when you order up your certificates and quizzes and stuff like that at the end. So when we have a slide that's kind of busy with a lot of words on it, generally that leads to a slide that has pictures. And so the key here for any kind of IEEE 1547 compliant inverter, and that could be for low-head hydro, for wind, small windmills, or solar, and we're going to be most specifically talking about solar today. These units act as alternating current sources, or AC current sources, when they feed the grid. And the reason for that is they use the grid voltage to stabilize the frequency of the current that they generate. In this way, if the grid voltage is lost, the current loses its synchronizing signal, it goes off frequency, the inverter notices that and shuts down. But if the grid goes away and you've got standby loads to power, then you can't do that anymore. So you need to switch functions with this inverter, and it has to now act as a voltage source. So that's the key. Current source when the grid is up, voltage source when the grid is down. And if your inverter doesn't do that, it's not going to work for you in a battery backup configuration for a grid connected system. Okay, they can also charge the batteries when the grid is up and when the sun is down. So if at night your batteries are low and the grid is still there, they can charge them up. This is becoming more and more important now because the IEEE 1547-2000 now allows people to set up agreements with the utility so that if the utility needs some extra kilowatts or kilowatt hours during peak time at 4 in the afternoon, they can simply contact your energy storage system and say, well, could you maybe spare about 5 kilowatts and 5 kilowatt hours of energy? And the little conversation goes on between your storage system and the utility, like about how much are you going to pay me for those kilowatt hours? And the utility takes a look at what it would have to pay for them if somebody else provided them, and the little negotiation takes place, and 100 milliseconds later, the system has agreed with the utility to sell them their 5 kilowatts and 5 kilowatt hours at some agreed upon price. So that's coming down the line, folks. That's going to be really interesting. And I think that's why a lot of people are gearing up. Most of the equipment now that is available is set up to be able to do this. Inverters don't need to do stuff like these special battery backup type inverters don't need to do fancy stuff like maximum power point tracking, because there are other boxes that do that. Now, in the modern inverters, the box that does that does happen to be within the inverter itself. But once upon a time, there was a charge controller that did this, that controlled the charge of the battery. Now the charge control function has been incorporated into the inverter itself. Usually also, they don't have to do ground fault detection and interruption or arc fault circuit interruption, because those are functions that take place in other boxes, but now in many cases, they've been integrated to the main inverter for the system. They need to be a part of a rapid shutdown system, and there used to be some really interesting implementations of that. Right now, there are a number of very elegant systems that what this means is if the fire department comes out and decides that they want safety up on the roof, they don't want a bunch of 450 volt DC running around down the house. They want to be able to shut it down at the location of the system on the roof. They flip one switch and it shuts down. So these inverters need to be a part of that process so that they'll shut down if the rapid shutdown switch is hit. And we'll talk a little bit about that. But once you got one installed, they don't smell bad at all, not compared to a natural gas 15 kW generator. You don't want to get within 50 feet of those sometimes if you're downwind. They don't smell too good, almost any kind of a gas generator. And they're just don't make a whole lot of noise. If I take my hearing aids off, I can't hear them at all. They hum a little bit when they start really cranking out the power. Actually, they don't even hum much anymore, because most of them don't have transformers anymore, and it's usually the transformer that does the humming. And of course, they save trips to the gas station, and they're part of a system that makes electricity for somewhere in the neighborhood of 6 cents a kilowatt hour. So folks are really jumping on these things. Then UL 1741 compliant, we've already talked about that. Okay, and a lot of them, you can connect a fossil fuel emergency backup generator if for example, the sun's behind a cloud for quite a few days in a row, you don't get quite as much electricity that way. Okay, so let's look at these battery backup grid connected systems. We talked about whole house and partial house, but we can refine it one step beyond that. There's DC coupled systems and there's AC coupled systems. Now, rather than read all this, I'm going to show you a couple of pictures and explain the pictures instead. Here's a block diagram of a DC coupled system. Starts with the PV array in that gray box in the upper left-hand corner. And this is one of the old systems. This is basically the components of a single box of one of the new systems, with the exception of the storage batteries that are always in another box. Okay, and the standby loads are oftentimes in a standby load panel. But in any case, we have the array up on the roof. We have a source circuit combiner box, because PV arrays typically come down 3 or 4 or more circuits from the roof, and they're combined together So you got a bunch of thin wires being combined so that the output of that source circuit combiner box is a set of fatter wires, maybe somewhere in the range from 8 to 6 to 4, depending on how many kilowatts you got up there. And maybe likely you'll have a surge arrestor in that at the input in case any lightning strikes anywhere near the array. You want to protect your equipment. The charge controller makes sure the batteries don't get overcharged, and if there's nowhere for that electricity to go from the solar array, the batteries are full and nothing else wants it, then it shuts down the array. Notice the directions of the arrows here. Some are unidirectional, some are bidirectional. And here we come to a couple of bidirectional. That means that storage batteries, we can either charge them or discharge them as needed. And the power that flows from that junction between the charge controller and the storage batteries, that can either go to or from the battery backup inverter. Okay. Once it gets to that battery backup inverter, that starts making electricity, and maybe a lot. The first choice for that electricity is to go down and meet the needs of the standby loads. Once the standby loads are satisfied, then any leftover electricity from that battery backup inverter goes up to the main distribution level. So this is a partial house backup system here, not a whole house. Anything left over goes to the main distribution panel where the loads in there now have a opportunity to use that nice clean solar electricity. And if everybody's away and nobody's running the dryer or the water heater or anything much other than maybe the refrigerator, there might be some electricity left over still. And if there is, that gets sold back to the utility. So that's the DC coupled system. It's got a single inverter, an array, and a few conditioning type boxes, along with some batteries, and another distribution panel for certain select loads like the microwave oven and a few other things, the refrigerator. Okay, then there's the AC coupled system. And by the way, there's a Q&A up there. There's one, let's take a look at what that question is. How do microinverters fit into the discussion? I am going to give you the answer to that at the end of the session because actually this morning I signed off on a system using microinverters and a 20 kilowatt hours of battery storage and about 12 kW of PV on the roof using microinverters. So yeah, they do fit, and Paul will have an answer for you probably in the second hour of the program, okay? And thank you for asking that question. And anyone else with questions, I'm going to be trying to watch my Q&A picture on top, and if I see something pop up, I'm going to just stop and try to answer it right away. This is supposed to be interactive. The best way we can do it today is if you type them into the Q&A box, because we've got a group of 25 people, and the Q&A makes it pretty straightforward to get to your questions. Okay, so here's AC coupled system. The first thing to notice here is there's two inverters. Now, one nice thing about this is that you may have started a system with an array on the roof and a direct grid connect inverter that connected to your main distribution panel and fed loads there while the sun was shining. And anytime the sun wasn't shining, it was up to the utility to supply those loads. But if the utility was gone, then you were out of business. There was no backup because the UL 1741 thing says if the utility is down, the PV has to shut off. It can't connect to the utility anymore. So here's what you can do now, and could do for a number of years, is put in a separate standby load panel and connect your direct grid connect inverter to that separate standby panel rather than to your main distribution panel. And then you add the three items on the right, which are basically what we just had in the previous system, a DC coupled system. So you add a battery backup inverter, And the fairly well kept secret there is that that AC out was actually a bidirectional connector. And you can also run AC back into that system. So in this particular case, when the sun shines, the electricity goes to the direct grid connect inverter, some of which are approaching the 99% efficiency level these days, whereas the battery backup inverters tend not to be quite that high, more like 95% efficient. So that's really significantly less loss. If you go straight direct grid connect to standby loads, those loads are getting some pretty efficiently generated electricity. That same standby load panel could have some additional electric feed from wind or low head hydro. And it still, if the utility is up, the part of the system on the right-hand side still works the same as the previous picture. That is, it comes in from the utility, meets the needs of the loads in the distribution panel, goes through the battery backup inverter and to the standby loads. And it's all a matter of how much solar you've got available, because if you've got lots of solar, maybe the solar will meet the needs of all the standby loads. And notice the bidirectional area to the battery backup inverter again, so that that extra electricity from solar can go to the battery backup inverter. And if the batteries don't need charging, then it's going to send it back to the main distribution panel. And if the main distribution panel has got all it needs from the solar, it'll send any leftovers back to the utility again. So we've got two different basic ways of doing battery backup, DC coupled and AC coupled. And the folks who are making today's systems, including the Enphase system that we had the question about, the Enphase happens to take the form of an AC coupled system. The Tesla system is basically an AC coupled system. The Generac system, on the other hand, is basically a DC coupled system. So we're going to take a look at all those systems later on, rather briefly, because I want everybody to understand exactly how the insides of these things function, because that's the way you're going to still understand these systems in 2025 when a bunch of newer kind of come out that none of us have ever heard about before. Okay, so let's move on here. There's some basic rules, and it's always nice if you want a battery backup system, and I can tell you that a lot of people don't even bother to do this anymore. But if you want to get it and have a pretty good idea what your system's capable of, the first thing you're going to do is list all your desired standby loads and the estimated power and energy needs. We'll see a table with that in a minute. There may be monthly variations in these loads. Maybe you got ceiling fans and refrigeration and different, more lighting in the winter, whatever. This is particularly important if you're doing standalone, like the off-grid type situation. You may want to even vary the tilt of your solar array so you can pick up more electricity in winter by tilting it higher. But for the grid-connected systems, the monthly variations are generally not quite of such great concern, unless you want to make sure you're making enough electricity after a nasty ice storm. Then this is something you might want to pay attention to. List the months when you most likely are going to need the backup power. Florida, August, September, October, hurricane season, most likely to need backup power. New York, New England, December, January, February, ice storms. I can remember our family up on Long Island just keeping their fingers crossed that they'd make it through those nasty predicted ice storms you all had planned for last winter. After you list your loads, then you can figure out how big of an inverter you need. And once you know those loads, you can figure out how much battery capacity you need. And once you know how much electricity you need, you can estimate how big the solar array has to be in order to make that much electricity. And if you want to, you can try to figure out how much electricity are you going to use at night and how much during the day. It just so happens that the AC coupled systems are really good for cases where you want to use a lot of electricity during the day and not quite as much at night, because then you won't need quite as much storage for night and you'll use a lot of electricity during the day, provided that the sun shines. So there's always a little kicker here that there's always some situations that could change things. Then you have to decide whether AC or DC coupling is best. We just talked about one instance where AC coupling might be best, but there may be others where DC would be better. And sometimes it's a matter of cost. Doesn't need to be a three-phase system. Not every system out there can be configured for three-phase, so you need to pay attention to that. So let's just, for the fun of it here, I hope everybody's having fun already. We're going to list some loads here. We would love for the refrigerator to keep going if the power company goes down. And despite the fact that you probably have your refrigerator on a 1500, a 15 amps or a 20 amp circuit, and you're listing it as 1500 volt amperes for the load, it's probably using only about 150 watts. Look at your yellow sticker and estimate your annual kilowatt hour consumption, divide it by 12, divide it by 365 or whatever to get your daily kilowatt hours, and figure out how many watts it takes to get that many kilowatt hours when the thing probably has about a 50% duty cycle at most. And 144 watts is pretty typical for a 21 cubic foot refrigerator. So that's about 1.5 amps, and this is going to be on 120, 240 connection. So we'll put that on L1. Then there's the microwave oven at 900 watts. That's 7.5 amps, goes to line 2. Washing machine, 1500 watts. Maybe not 1500 anymore for the more efficient ones, but let's say it is. That would be 12.5 for line 1. Computer, 2.1 on line 2. Lighting, say you got 120 watts of LED lighting. And so everybody can read the table here. And so what we're looking at is the totals that are important. The total load in watts is 3,424 if everything is on at the same time. And we need that in terms of the power rating of the inverter. The maximum current on line 1 is going to be 16 amps. Maximum current on line 2 is going to be 12.9 amps. And if they work exactly the way we think they will with our estimate here, it will use up 7.65 kilowatt hours a day. Okay? And I've seen many a system designed with basically this set of operating parameters. Because an 8 kilowatt hour battery pack used to be pretty common with 8 6-volt batteries rated at a kilowatt hour apiece 10 and 15 years ago. That's what you got. Okay, so if you do the process this way, you're going to know exactly what you can expect from your system. Okay, so now we need an inverter, and remember back there we needed at least 3,600 watts. Or 3,424 watts, okay, and it has to be able to pass this through from the utility when the utility is up and it's nighttime, okay. It needs to be able to pass through 16 amps to meet the load on line 1, a little bit less on line 2. So we look for an inverter that will pass through 50 amps. Well, that's because that's what most of them will do when the grid is up. And when the grid is down, supply 16 amps. Okay, so let's see what we might find. More than likely, it'll use a 48 volt battery if it's a 10-year-old system, and needs some external storage. More than likely, if it's a battery pack that's currently being used in the integrated systems, it's going to be more like a 400 volt battery pack. But in any case, 48 is what it used to be, and this is a number. And so when you're paying attention to your design, you're going to look at what's the power rating and the voltage rating and the current ratings on your battery packs. Okay, and the inverter has to be capable of charging batteries from the grid if the array is down. Okay, like at night, and most do that. And It might use some external DC and AC component enclosures like that spare backup load panel that we showed in a previous drawing. The AC enclosure might house some of the standby circuits. The DC enclosure might be where you combine all of the different things from the array and the batteries and the charge controllers and so forth, and have some separate circuit breakers for all those things so you can shut them down if necessary. Thing about these is they were programmable, and a lot of people like to play with them, and it's amazing how many batteries got burned out too soon because people tried charging them too fast. But people who've left their settings the way they're supposed to be, a friend of ours has had their battery pack now for 12 years, and they're going strong. He doesn't notice any degradation. So if you treat your battery backup system properly, they will treat you properly as well. So let's look at some features for some inverters. You're going to see specifications, all right? And these are properties you'd like to have. And what I'm going to do is take a look at some specs. The key thing here at the bottom is that the inverters need to be UL 1741 compliant, okay? And usually what they do with AC coupling, we're going to come to those, is the inverter needs to be able to tell the backup system, or the backup system needs to tell the inverter one way or another when it's time to shut down. And the inverters do that by changing frequency, and that sends a message to other parts of the system. All right, so here's two models that were available a while ago, and you can still buy them now if you want to do things the older way. Both of these, I think, have been incorporated into some of the newer systems that have it all in one box. But here's a 4,000 volt ampere system that has a continuous power rating of 4,000 volt amps, although it will kick out more than that if you want to start a motor when it's running independently of the grid. And then its big brother, big sister, uncle, who knows, is twice as big. DC input voltage range on these happens to be 40 to 64. Their output is 120/240, and you can unbalance that up to about 80%. The AC output current is obviously twice as much for the bigger one. You can bring in a lot of AC input current because most of it gets passed through to the standby loads. In each case, it's still 50 amps, whether it's an 8,000 volt amp or a 4,000 volt amp available for backup. Input current is twice as much for the one that's going to give you 8,000 volt amps. So you can see at 48 volts, 184 amps, that's pretty significant DC input current. You're using pretty fat wire to bring that in, and usually you're going to use battery cables with that are more flexible and need special connectors, in fact, rated for batteries. So these are a couple currently available inverters. Buy them quickly though, because they may not be around for too long, although hopefully they'll be providing parts for backup and for repair and warranty repair. Okay, let's see. We've got a question up here. Let's take a look. How do we take into account loads with high startup demand, such as a well pump? Oh, perfect. Let's take a look at these specs. The timing is perfect. Notice the instantaneous power for 100 milliseconds on a 4,000 volt amp is 8,500 volt amps. So you get an extra 4,500 volt amps, or in other words, twice as much. Because that's exactly what they're thinking about as a surge current. It'll give you 6,000 volt amps for 5 seconds, and they'll give you 4,500 per 30 minutes. So yes, they thought about that motor that needs to be able to have a starting current, and most of these you know, top quality battery backup inverters take that into account, and so they can start your motors. Okay, so let's, in this particular case, the 4,000 volt amp unit is big enough to do what we need for it to do based on that list of loads we just had. So let's move on and see where we go from here. Now we need batteries. And daily load requirements, 7.65 kilowatt hours. So that means we need to take into account some efficiencies here. And there's a little wiring efficiency between the inverter and the batteries. And the inverter efficiency itself, in this particular case, their efficiency is 94%. So therefore, in order to get 7.65 kilowatt hours out, we need to deliver to them from the batteries 8.3 kilowatt hours. Okay, that's what the inverter needs from the batteries. The amp hours from the batteries to the inverter is simply the watt hours divided by 48 volts. In other words, 172.9 ampere hours. So now we think about this for a while, and if we're looking at lead acid or even lithium technology, it's generally a pretty good idea not to discharge much below 80% of the total available charge. Now you can do that with lithium without damaging them much, but once you get down to 20% state of charge, their terminal voltage starts dropping much faster than it did before you got down that far. So it's kind of nice to allow that extra cushion. And therefore, if you want to make sure you only use 80% of the stored energy, then you're going to have to increase your battery size again. So we divide that 172.9 by 0.8, and you end up with 216 amp hours worth of batteries you're going to need at 48 volts. Okay, so that's what you need to do what you want to do with the list of loads you have. All right. So if you just need 1 day of storage, then what you like to do is think about the fact that the faster you discharge a battery, the less useful electricity you get out, because there is internal resistance in these batteries. And the higher the current you draw, the more I squared hour power loss you have inside that inverter. And inside the battery itself, not the inverter, inside the battery. So instead of the battery running loads, it heats itself up instead. So for 1 day's worth of use of the battery, that means you want to take 24 hours to discharge it, ideally. So let's see what that means. That means you need to have, first of all, a deep discharge battery that is used to store quantities of kilowatt hours as opposed to being able to start your car with kilowatts. And most of folks these days are going with lithium. Every system I've signed off on in the last 5 months have been a lithium battery pack. Probably only signed off on maybe 20 or 30, something like that. And they all call for the lithiums these days. So, and there are a lot of advantages to lithium, one of which is you don't need ventilation with it because it doesn't give off hydrogen when it charges. So 216 amp hours at 6 volts is a fairly common battery. And if you multiply 6 times 216, you notice that that's a little over about 1,300 watt hours, which if you use just 1,000 of those, that's a kilowatt hour. So this is basically a kilowatt hour of storage that we're looking at here for one battery. And if we have 8 of them in series, then we've got 8 kilowatt hours of useful available electricity. Okay, so with lithium battery packs, you just verify the voltage and the kilowatt hour ratings. The ratings are typically somewhere in the neighborhood from 2 to 3 for per element, but then you stick 6 of these 3 kilowatt hour things into a single package, and you've got an 18 kilowatt hour battery pack of DC. So let's check the battery discharge rate. And again, we were talking about 24 hours to remove 80% of the battery charge. So what's the power you can use? Well, that means that 172.8 amp hours is 80% of the charge. And if we use that in 24 hours, it means we can draw continuously 7.2 amps of DC. And 7.2 amps times 48 volts is 345.6 watts, which is presumably also the AC then that's being delivered, since this is the 345.6 that goes into the inverter. So this is essentially saying, if you can run pretty much 350 watts for 24 hours with this particular battery pack. But who runs their electricity like that? I don't. I bet you don't. Now, for lead acid, it's nice if you can limit your discharge to at least taking more than 5 hours. And again, because if you discharge in less than 5, you lose quite a bit in terms of heating the inside of the battery and not being able to use it to heat your coffee in the microwave oven. So this means if we want to discharge them in 5 hours, we can pull up to 34.6 amps. So that's 1,660 watts, and 1,660 watts will run a lot of appliances. Anything on a 20 amp circuit, you can do 1,660 watts, because the 20 amp circuits is just about that. 16 amps at 120 volts. Is a little bit more than 1,660. But in any case, it means that without making your batteries too unhappy, you can draw up to 1,660 watts. And most of the battery packs do have a power rating that they do not want you to pull more than a certain amount of power out of any particular battery pack. And that's one of the things you look at when you look at the specifications of the battery pack. Okay. So it's a good idea to try to schedule standby loads so that you don't use more than 1,660 watts at any one time. And if you do that, your batteries will be appreciative and they will give you more electricity than they might give you if you don't do that. So there's always a possibility of adding more batteries. And the more batteries you add, of course, the more kilowatt hours you can get, but also the more watts you can get. Because at that same discharge rate for twice the storage, you could go up to 3,320 watts instead of 1,660. All right, so that is an option. The system I worked on this morning used 2 battery packs at 10 kilowatt hours each. So that means they take advantage of them and get double the power rating to feed, and now they can feed loads on a 40 amp circuit breaker rather than just a 20 amp. Another nice thing about lithium batteries, you can discharge them almost 3 times faster than lead acid batteries with the same amount of loss. So the internal resistance of lithium batteries is a lot smaller than the internal resistance of lead acid. So you can charge them faster and you can discharge them faster without damaging the battery and without losing too much to heating up the batteries. Okay, so now we know how many batteries we need. We need about 8 kilowatt hours worth of batteries. We know what our loads are. So now we need to provide that 8 kilowatt hours a day for the batteries from the solar. So how are we going to do that? Well, here's our 8.3 kilowatt hours a day that we need to deliver. And with lead acid batteries, you lose energy in the charging process and you lose it in the discharging process. So the so-called round trip efficiency for lead acid is generally accepted to be about 90%. And again, it's less than that if you discharge them too fast or charge them too fast. And it's a little better than that if you do it slowly. The comparable number for lithium is about 96%. So again, it's consistent with the observation we just made. So since the round trip efficiency is 90%, that is, you only get 90% of what you put in is what you get out. Sounds a lot like the stock market. Well, maybe not recently, but certainly it's had those times. We take our 8.3 kilowatt hours a day that we actually need to deliver to the inverter, and we divide that by 0.9 and get 9.22 kilowatt hours a day that we need to deliver to the batteries in order to get the 8.3 back out again. Okay? And there are losses between the array and the batteries. The array loses temperature, it gets dirty, dusty. There are wiring losses, charge controller losses, and so forth that once upon a time people had to pay attention to. Now you simply, because these losses, they happen pretty much no matter what the array feeds, whether it feeds a straight grid connecting inverter or just the charge controller for the batteries. So it is very easy to do a simulation on a program such as National Renewable Energy Laboratory's System Advisory Model. And all you have to do if you want to play with this, if you're tired of nighttime TV, is go to NREL-SAM, download a copy. They're free. We taxpayers paid for it. And you can do such fun. You can have such fun trying to figure out how much electricity you can get out of your photovoltaic array by playing with SAM. Now, there are fancier, more expensive systems out there that the investors use to make sure every 1 or 2% makes a difference for an investor. But just to get a rough idea, it's pretty reasonable given that the weather is fluctuating every single day of the year. May the 17th next year is probably not going to be the same as May the 17th this year. So you can't really predict on a day-to-day basis, but on a year-to-year basis, you can get a fairly good idea of averaging things out. And that's kind of what NREL-SAM does, but it actually does a calculation. He does 8,760 calculations for every hour of the day through the year, taking into account the efficiency of your modules, the temperature coefficients of all the equipment, the efficiency of the inverter, all kinds of stuff. So it's a really fine piece of software. I highly recommend it to anybody who wants to toy around with PV, or if nothing else, you're just tired of watching TV. Here's an analysis for array size. If you're looking at Tampa, Florida, with a roof slope of, with a 412 slope, 18.4 degrees, we are wanting to get 9.22 kilowatt hours a day, which would be 286 kilowatt hours in a 31-day month. Okay, so if we start with the SAM PV watts model, that simply does not, you don't have to tell it what kind of modules or what kind of inverters you're going to use. It does kind of a generic analysis. And if we analyze a 1 kW array for Tampa, tilted at 1843.43 degrees, facing south, well, not even, yeah, tilted at 18.43, which means that the array itself is not necessarily pointing right at the sun. It's simply mounted essentially flat on the roof, actually about 3 inches above the roof with a rack mount, or I mean a surface mount. NREL-SAM says you can make 1,475 kilowatt hours a year with this system, and in August you'll get 134 kilowatt hours, and in September you get 119, and October you get 121 for 1,000 watts on the roof. Okay, well, that's not quite what we want, is it? We want 286 kilowatt hours, and we'd like to have that 286 in October as well. So let's do it for September to start with. Bring September up to 286. And The reason for that is because September has only 119 kilowatt hours, while October has 121. In other words, it's a little more cloudy in Tampa in September than in October. So to get this total up to 286, we just need to multiply by 2.4. 286 divided by 119. So we end up with a 2.4 kW array. Now that's pretty simple, wasn't it? That'll give what we need in September. But what about December or January, and for that January snowstorm over in Tampa? Well, first of all, you get 3,543 kilowatt hours a year, 322 in August, 286 September, 290 in October. So is that what we're looking for? Well, if we want 9.22 kilowatt hours a day every month, then we need to look at the other months. And it turns out that January, February, November, and December, you don't get your 9.22 kilowatt hours a day. So to up it to that for every month, then the December production has to go from 222 up to 286. 222 is what we're getting with the current simulation. We're going to have to bump it up to 286 to get what we're looking at for our load calculation. So again, 286 over 222 says make it 1.29 times bigger, which so now says we should have a 3.1 kW array. Well, 3.1 kW these days is small change. I analyzed 11 systems this morning, and every single one of them was more than 6 kW. Some went as high as 18 kW. So we're not, 3.1 is a small array. But that 3.1 kW array is enough to give you those kilowatt hours you need for your backup system every month of the year. All right, and the annual kilowatt hour production to the batteries will be 4570. And once the batteries, if you don't use this in the batteries, that's 4,570 kilowatt hours is now available for use by your regular loads. If there's no emergency, then all of this electricity, you're just going to use it. So that subtracts from your electric bill. And do the math. I don't know, New York, what are you paying? 18 cents a kilowatt hour? 4,570, 4,570 times 0.18, that's $822.60 a year you're getting back on your electric bill. So, or that you're not paying on your electric bill. So that's not a bad return on investment. Now you just have to figure out how much the system's going to cost. But we're not doing economics today. It turns out, though, that actually the economics of these systems gets better all the time, even with battery backup, because now you can do that deal with the utility where the utility will ask your system if it will spare them some electricity. It's going to do that with electric cars as well. And whoever heard of electric car paying for itself by selling electricity at a high price during the day and then buying it at a low price during the night? Or maybe just the opposite, when the world goes all solar. Well, maybe that's a little optimistic because there's going to be a lot of wind and hydro and other stuff mixed in as well, and some geothermal as well. I need to make sure I mention geothermal every time. I got crucified one time by one of the participants for not mentioning geothermal. And I don't know whether that person was from Iceland or Yellowstone Park, but yeah, there is some geothermal out there, and some areas are really heavy on it. Let's look at some constraints on the array. With this particular system, you can't do more than 3,200 watts at the output of the charge controller for a particular 60 amp charge controller. Okay, that doesn't mean you can't use two charge controllers, but if you have only one, maximum input voltage of 150 volts. And so the array could actually be more than 3,200 watts by about 15%, and you're still okay. because the charge controller output current is limited to 60 amps. Now, one thing that you learn when you're doing solar for a long time is that solar modules almost never perform at their rated level, because as they get hot, their power production capability goes down. And if the sun isn't shining on them at full intensity, their power production goes down. So the only meaningful number with solar is how many kilowatt hours per kilowatt can you make in a year's time. And that's how you do your economic analysis, is based on the kilowatt hours, because that's what you're buying for the most part, unless you're on a demand rate. Okay, so let's go a little further. Have to have the open circuit voltage less than 150. Keep the maximum power voltage more than 65 for the. All right, well, you know, I'm going to go through this kind of quickly, because these are all things that folks had to be concerned about 15 years ago when designing these systems. But thanks to various things, like, as somebody said, Enphase, they take the worry out of it. So here's some possible module choices. Okay, fine, there's a bunch of them out there. And these are the ones that are kind of out there now. Although who's going to, they're pretty hard to find a 235 watt module, but the 320s and the 300s are there, and the 265s are even hard to find now these days. But you pick a module, and what we're looking at here, folks, is process, not necessarily the very specifics of what was available 2 years ago, but we're looking at the way you can go about understanding how this thing is working, so that you'll be sure to match up your components in your system so you get the performance that you're looking for. And that's really what it's all about. Okay, so here we've got some module choices. Fine, we choose one, do temperature corrections, and you use the temperature coefficients. As they get colder, their voltages go higher, their power goes up. So the colder they get, the more power they give. The warmer they get, the less power they have available. Their rated power is at 25 degrees C. And I'm looking out my window at more than 25 degrees C right now. And when the sun shines on them, they get up easily to 50 degrees C. So they do lose up to 15% just from getting warm. Okay, so we pick a module. Looks like B's or C's would be nice, but again, we're just doing a basic idea of how many modules are we going to need. And we have to, like, if we use module B, we would use 10 of them, and we would use 5 source circuits with 2 modules in each source circuit, and then that way we get 3,200 watts for an array. If we use module C, then we can get 4 source circuits with 3 modules in each source circuit. So in other words, the open circuit voltage of module C is not as high as the one in module B, because it has fewer cells. The one in C probably has 60 cells, whereas the one in B, an open circuit voltage of 70.9, that's what you get in a like a 96 cell module. Okay, so not likely we're going to use a B, probably going to use C. So anyway, whichever fits best. So that's another constraint. You got to look at your space constraint. Most modules are about 1 meter by 2 meters. Some are a little bit shorter than that. And you kind of fit what you can in the space available on the roof. Okay, well, wire sizing. You know what? I'm not going to spend a lot of time on wire sizing. I'm just going to show that these are some of the rules. And all of the rules for wire sizing are in National Electrical Codes, Chapter 690. So these rules all come out of 690. And basically what you're going to end up doing is your source circuits, you're probably going to use number 10 wire, because historically that's what everybody does, whether they need it or not. And this wire size, but in the output circuit where you've got almost 60 amps, then you're probably going to use number 6 wire. Okay, that's where you've contained all, or you've connected all of your source circuits together to have a single output. Okay, and number 12 and number 14 wire meet the ampacity requirements. So the only thing you need to be concerned about is whether they meet voltage drop requirements. It's generally a good idea to try to limit voltage drop to less than 2%. My company is working on a slightly larger system that uses about 13,000 modules, and they're trying to limit the source circuit voltage drops to 1% and the output voltage drops to 2%. And as long as you compact things enough or use fat enough wire, you can do that. So again, if you really are interested in this, you can go through these calculations in more detail if you just order up the PDFs. Okay. The only correction factor we're using here, then just a list of all the wire sizes for the system, and they're based on the continuous duty correction of 125%. Okay, so this is typical wires and circuit breakers you're going to be using for this particular setup. Voltage drop, if you feel like you want to do the calculation, you can do it, pretty straightforward. And here you can see the kind of percent voltage drops, how far, and what I'm giving here on the right-hand side is you can go 60 feet with 2% or less voltage drop with number 10 wire on the PV source circuits. And that's because they're relatively low voltage. They're in the 120 volt range. If you're doing a utility scale system, you're probably going to be operating at 1500 or about 1200 volts. So your voltage drop is only going to be 1/10 as much as it is for these circuits here. Or the other way of looking at it is you can go 10 times as far with the same voltage drop if you increase the voltage by a factor of 10, which is now happening behind the fence in utility type arrays. Residential limited to 600 volts, commercial 1000 volts. So, and if you're behind the fence on utility, you might be going 1500. Okay, so again, here's just some numbers for you. So I'm not going to look at every single one, but it's something you can take a look at later on if this is something of any significant interest to you that goes beyond getting the extra 2 credits of continuing ed credit. So here we lay the array out, and we have 12 modules, and we try to lay them in the middle of the roof to the extent possible, because they're on the edges, the wind pressures are higher, and you have to be a little more fussy about holding the modules down and make sure they'll withstand the upward lift, which in some cases, like down my area here in Florida, it's not unusual to see 65, 70 pounds of uplift, 65, 70 pounds per square foot of uplift, and you have to design to make sure they don't blow away. Obviously, if your battery backup modules blow away, they're not going to help you much after the storm goes away. So you do a wind load calculation. Again, I'm going to click through this. If you want to get serious about wind load calculation, ASCE 7-16 from 2016 now finally has a procedure in Chapter 29 specifically aimed at calculating the wind load on solar modules. So you can follow that procedure and you come up with the kind of numbers that I'm mentioning. But here's some numbers I'm going to just click through fairly quickly. Tampa's got 140 mile/h design wind speed for a Category 2 building, which happens to be now a risk Category 2. And that's something that people kind of live in, but it's not of essential importance. It doesn't have caustic chemicals or toxic chemicals, which if the building blew away, the chemicals would flood the neighborhood. It's not a hospital, it's not a police station. It's a Category 2 building, okay? The Category 3, Category 4 are going to have a higher design wind speed than Category 1, which is out in the country where it's highly unlikely any life will be endangered if the building has some damage, then the design wind speed is a little bit less. So lots of interesting rules these civil engineers come up with, mostly based on very good wind tunnel testing. And their procedures are pretty interesting, I have to tell you. Here's this is ASCE 710 wind load, okay? If you use a 716, it would be about the same. And it comes up with a downward force and a maximum downward maximum lift. And generally, the upward force or the suction or lift force on the panels is much higher than the downward force. So it's this lift that you want to be paying attention to, and you have to make sure they're held down. Now, the neat thing here is you're going to hold these things down probably with 3.5 to 4 inch stainless steel lag screws. Maybe some other material, but here we like stainless because of the salt water and salt air. And imagine if you screwed down your roof decking with 4 inch lag screws rather than putting nails in it, whether it would blow away or not in a hurricane. So a lot of people don't realize that putting these modules on the roof makes their roof more secure in a hurricane. In case you're out selling PV systems this afternoon, I'm not really in the sales business. I just do the engineering. But some interesting side benefits that happen. So in any case, if we got 17.5 square foot module, and again, that's a small one because most of them now are about 22, but 6 modules is 105 square feet, and at 32.3 pounds, that's 3,392 pounds. And so if you've got, I guess, I don't know why I passed up. Anyway, if we have the force per bracket, then this mounting is going to be 283 pounds. And if we use 5/16 inch lag screws, Southern Yellow Pine pull strength with a factor of 4 safety is 332 pounds per inch. So that means if it's embedded less than an inch into the trusses, we're not going to blow away. So these systems can very reliably be mounted to a roof. And as long as the roof is designed so it won't blow away, the PV system on the roof is not going to pick up the roof and blow away with it, because the load that is impressed upon the PV system is the load that is taken away. That same load basically is on the roof, because after all, the PV system is on the roof. So distribution panel for the standby loads, again, it's just going to have to be big enough to hold the loads. Pretty straightforward. The important thing is if you take some loads out of one panel to put in another, if you have any multi-wire branch circuits, okay, then you got to make sure you put both circuit breakers. Say you got 2 circuit breakers side by side, one does the master bedroom, one does the front bedroom. If you're going to power up the master bedroom after a hurricane, then you got to power up that front bedroom too, because you have to pull both sides of that neutral. Otherwise, the neutral is going to be overloaded. Same thing if you got a 3-phase system in a bigger building. If you take one load that's important, you got to take the other 2 on that same to balance the loads on the neutral. Okay, just some thoughts there, and something that's not a major well, it is a concern. When you do create a second panel, you need to make sure that you move every load that has a common neutral along with that common neutral into the new panel. Equipment grounding and bonding. Again, all the rules, NEC 250, and you know, you just follow the National Electrical Code on the grounding for equipment grounding conductors, grounding electrode conductors. Rules are all the same. And so here's a schematic of a 240 volt backup system. And you got the 6 modules on the roof, source circuit combiner box. You got 4 different circuits with those 6 modules. Combine them all into one. They go through the ground fault detection interruption. They feed the charge controller 60 amps in, 80 amps out. Why is this? Because the voltage, the input voltage of the charge controller is about 8/6 as much. So in other words, the charge controller is like a transformer in a way, except it's a DC to DC converter, and it converts a higher voltage into a lower voltage, but the power in equals the power out with maybe 1% loss at best. So therefore, you put in 60, you get out 80 at a lower voltage, just like a transformer that's transforming high voltage to low voltage. You go from low current to high current. All right, all goes to that little positive bus bar, goes to the batteries, goes to the inverter, whichever one wants it the most gets it. And the charge controller is responsible for making sure that voltage doesn't go too high, because that would mean the batteries are overcharging, and then they are not happy with that. So the inverter sends it out to an AC component enclosure which has a bypass switch in it. They used to do this with inverters because they weren't really sure. They want to make sure that you'd get power to the distribution panel, the bypass panel, even if the inverter went bad. So they had a mechanism with an interlocking switch so you could bypass that inverter for maintenance purposes. Again, an obsolete piece of equipment. You rarely see these anymore, but that's the history on it. So on the AC side here, we're only showing a single phase, but this is in fact a 120/240. So the single pole circuit breakers are actually two pole. And normal operation, the bypass switch is open on top and closed on the bottom, so that you don't go directly from AC in to AC out. You go from AC in to the inverter, let it do its thing, and then to the AC out. Okay, so a little quick wrap up on this 80 volt side. So no, you need arc fault protection. Okay, again, I'm going to click these because we're time is moving on here. We only got 45 minutes. And these are typical settings for the charge controller back in the days when you had to do that. Okay. I'm going to go through this one kind of quickly just to show you that the way we did that last one isn't necessarily the be all end all. We started out by what we wanted to do. Now here we're going to say, well, we're going to put as much solar on the roof as we possibly can, and then we're going to figure out what it'll back up. All right, so let's do that. Okay, we're going up to Burlington, Vermont on this. Nice new roof, 45-degree slope. Okay, and again, we're doing the same basic stuff we did before. We're going to assume we got 24 300-watt modules that we can put up on the roof. Okay, and this is the specs on those modules. All right, so let's see what the array might do. And here's what your simulation looks like when you get that NREL SAM. It tells you your month by month expected output of that array. And what this is the AC output of the inverter connected to the array. Okay, but in this particular case, it's going to be the AC that is the output of the charge controller. And it's not going to be AC, it's going to be DC, which then goes to the inverter. So in any case, this is what you've got available from the sun. Let me look at my Q&A up there. Oh, no, that was up there under more, I think. If you want to chat, please use the, let's see, I just want to, yeah, okay. Thank you, Hisham, for monitoring the chat box. So yeah, let me remind you again, I'm watching the question and answer box. So when I see a question pop up there, I'm going to jump on it as soon as I see it. I do have to bend my neck way up to see that, but it's worth it. I'm happy to do it. So here's the deal. With this array, we can get 9,191 kilowatt hours out of the array. So what can we do with that 9191? Well, now we have to work backwards and look at where are the losses. All right. So if we have 10% battery loss, 6% inverter loss, 2% wiring loss, then we can get 7,620 kilowatt hours per year, or 20.9 kilowatt hours per day on average to the loads. Okay, so that's not hard to do that, is there? These are nominal losses, the same losses we used the last time. 10% in the battery, 6% in the inverter, 2% in the wiring, and all the rest of it can go to the loads. Okay, 20.9 kilowatt hours a day. That's more than we had before, isn't it? But we didn't have a 7.2 kW array. So now we can figure out what kind of standby loads we can do. And we want to do the refrigerator, microwave oven, washing machine, computer, lighting too. But now we're going to add a mini split air conditioner, okay? And it's appliance circuit here, and we're going to throw in a TV and a fan for a furnace to make sure we can heat up. Then we've got some fuel for the furnace. So now we're up to 7,864 volt amps of loads connected. Line 1 and line 2 more closely balanced at about 34 amps each, and a load of 16.2 kilowatt hours a day. In other words, just about twice the size of what we had before. And in fact, the array size this time is about twice the size of the array we had before. So you can see that whether you work it frontwards or backwards, you're still going to get pretty much the same result. And so this means if this is all we can do with that roof, then this is what we can do on a battery backup system in terms of standby loads. So you can do the calculation and know ahead of time what you might be able to expect. Okay. Again, battery selection, same thing. We now need 16.2, but we have to go through the same procedure. Okay, and I'm trying to go a little faster here because I just this week added some of the newer systems. I want to make sure you see what's out there now. Take the place of what we're looking at is basically these parts we're looking at all have to be a part of those newer systems, but they put them inside a single enclosure rather than 2 or 3 that you have to nail onto a piece of plywood on your wall. Okay, so the source circuit design, same game. Here's nice formulas for you in case you want to ever do this calculation. It gives the 0.003 is the temperature coefficient of the open circuit voltage of the modules. And I guess this is assuming generally the folks who are taking a battery backup design course have had some experience with straight grid connect or with PV one way or another. So this is your temperature coefficient for the maximum, the open circuit voltage. And you'll notice that it starts out at 40.1, but when it goes down to minus 30 degrees Fahrenheit, which is minus 34.4 Celsius, the voltage goes up from 40.1 to 47.25. All right, and then for the maximum power voltage, that's the voltage where the solar array delivers maximum power. You want that voltage goes down as the array gets hot. And we're saying the maximum temperature might be 158 degrees, which is 70.3 degrees Celsius. So it starts out at 31.6, but by the time it gets up to 158, it drops down to 25.2. So you got to make sure you've got enough there. Oftentimes you can't track maximum power for less than a certain value. And so this is useful. Now, of course, with microinverters, they take care of that for you, and you don't have to do any of this stuff. But this is basically what the boxes are doing for you that you don't need to do. So anyway, this particular system will work just fine with 8 source circuits of 3 modules each instead of 4 like we had in the last one. Basically, it's twice as big as the previous one. Basically, charge control and source circuit combination combiner box. We need 2 of the combiner boxes because the one we used the first time was as big as it could go. Actually, we don't. We need 1 because there is a source circuit combiner box out there that will do 8 circuits. And there's a charge controller. Well, we kind of maxed out on that, so we're going to need 2 of those. So anyway, 2 80 amp charge controllers probably be needed. All right. And an inverter, which you're probably already guessing will be the second one on that first list. And then a combiner box to combine the outputs of these circuits. And usually they use 20 amp circuit breakers, sometimes 20 amp fuses, but mostly DC circuit breakers now. So again, here's the inverter. Again, same story. Same story for calculating wire sizes. Again, we're still using number 10 on the source circuits, but now for the output circuit, it's a lot more current, it's twice as much. Okay. And check the voltage drops. Again, same sort of thing. Size the circuit breakers, and here's the typical circuit breakers you'd be using on that particular system. All right, let me see how we're doing on time here. 3:22. All right, we're going to make it okay and have time to talk about some stuff. Let's just look, see any no Q's and A's. And only half the people have dropped out. The others who are sleeping at least left their computers on. No, it looks like folks are still here. I'm hoping that everybody's going to get something useful out of this afternoon. I tend to get enthused about it because the first system I built was battery backup, except that it was basically somebody was afraid when the year 2000 came in that all the predictions were going to come true and all the computers would get messed up and we'd lose all power and lose all water and lose everything. I still remember waking up that sunny morning and noticing that nothing had changed. It was all just like it was the morning before. So anyway, here's your sizing of the circuit breakers for that 8,000 watt system. And here's your schematic diagram for it, okay? For the DC side. And you can see we've got 8 source circuits, three modules each. Go to those combiner boxes, box A and box B. They then feed this DC control side with ground fault detection now for 2 poles, because we now have 2 charge controllers, a bigger set of batteries, and to the DC input side of the inverter. Okay, there's your schematic. Here's the AC side. Utility meter, main disconnect, 60 amp breaker feeding the main distribution panel. Then we've got the inverter bypass switch here that is now 2-pole bypassing in case you want to take the inverter out of service. The standby loads down below, the AC in, the AC out. So that's the AC half of this system. Rapid shutdown has been required now since 2014, I guess. In 2014, National Electrical Code said you have a certain functional requirement. We don't care how you do it. And here's one of the early bird solutions that came out. And these folks had been in the standalone system business for a long time, so it was fairly straightforward to them to come up with this. It was basically a bunch of contactors that shut things down based on turning off that main switch there. There are other ways of doing this now, and I'm not sure how many of these are being sold. I can say that of the 500 or so systems I've looked at in the last 4 or 5 months, I've not seen any of these. So I'm not sure how popular they are, but in my neighborhood here, other things are being used instead. Let's look at that DC coupled system, see how we might make it a little simpler, okay? Because one manufacturer, and in particular, I guess I can say that I'm not advertising here. I'm not saying any one manufacturer is any better than any other. But Generac has a system. The generator, the fossil fuel generator people have noticed that a good way to avoid going out of business is to get into the solar business. Very clever of them. In any case, they've done this. You can have a PV array going into their little black box, and at 600 volts instead of 150 volts, that means you can string out more series modules and have bigger voltages, less percent voltage drops. So it's a desirable thing. 600 volts is the maximum allowable for residential. Inside this box is a 5 kVA 120 volt battery backup inverter. It has 24 amps of continuous AC current out. There's a source circuit combiner with 20 amps of the charge controller. Actually, they now have a 7600 watt box that does 32 amps. Charge controller has a wide range of maximum power point tracking, integrated arc fault, ground fault, PV utility, battery charging, all that stuff that we had in about 5 different boxes is all in one box. And all you have to do is connect your batteries up to this. And by the way, the batteries now don't connect with 175 amps at 48 volts. They connect up with maybe 30 amps at 400 volts instead. And since it's an integrated package, it's okay to do that. You don't have these fancy rules about extra switches for every 48 volts of batteries. Backup panel connects directly, and the main panel connects directly. So this is pretty slick operation. Let's take a look at one. You start with the utility. Oh, this is a slide I added yesterday, I forgot. Okay. All right, so we're going to start with the utility here. And you got a main distribution panel with the main breaker. And then we add this fancy inverter. And this is our connection to the utility. And we add some solar. Okay, that's the solar connection. We add some storage. And we add a standby panel. And there's that system, the schematic of that system we just talked about on the previous page. And one of the reasons why I love giving these webinars is that I love drawing some of the pictures. I'm sorry the audio wasn't on. I'm sure everybody will be clapping at this one, but let me look to see. I don't even see any Q&As flashing. Maybe it's not as good as I hoped it was. Well, anyway, hopefully this explains that how much more simple this whole thing. I mean, this DC storage is all in one box. All the charge controllers, everything, the battery management system, it's all in that box. You get DC out at about 400 volts to the inverter. PV comes in at about 400 volts. Notice it's all in the same bus bar here. We can connect more PV or more storage. We got 4 circuit breakers here for connecting stuff. So, and then you do the same math if you're really curious about what this thing will do for you, depending on the size of the PV, the size of the storage, and the kind of loads you've got. Now, one thing that's happening now is people are forgetting to do that. And sometimes they're putting way too little storage and way too much PV to have an efficiently operating system. So you got to be careful. That's why I wanted everybody to see those rules at the beginning, because it's really easy to mess up these systems if you don't pay attention to what the manufacturer says. Now, the inverter manufacturer is going to tell you that the inverter has a rated, or the DC storage has a rated output power. And you don't want more than 156 of that, 150% of that rated output power of the DC storage That's all the PV you want. Otherwise, you're going to be wasting your PV, partly because the connection to the utility won't let it all go through. So, if you don't use it all on your standby loads, then it gets wasted. At least some of it will. So you got to be careful on your design to get it right and not have too small a storage or too big of a PV to go along with this particular inverter and these particular standby loads, okay? Here's some Q's and A's. There's two of them now. Let's see what we got. Oh, thank you, anonymous attendee. James, you'll get copies of all the slides. Just request the copy of the presentation and you'll get a PDF. You won't get it where you get to add these pieces all by one at a time, but you will get them as one system, okay? Okay, moving on. Let's see how we're doing for time. 3:30. We are doing okay. Here's an all-in-one DC coupled system. Here's what it looks like. There's the inverter, standby load panel, and a couple of battery cabinets. These battery cabinets are each capable of 18 kilowatt hours of storage. So there's 36 kilowatt hours of storage here. And you notice it's pretty high voltage because that conduit joining between the two is coupling the power from the one on the left to the power to the one on the right. And that size conduit is certainly not going to accommodate 4-aught copper or 4-aught aluminum or 2-aught copper or whatever. And that inverter there is rated at 7,600 watts. When I first saw that, I couldn't believe it, but there are no transformers in these. So they are light and efficient and very good. And standby loading panel is got some control stuff in there as well, but most of it's in the inverter. So here's some of the specifications here. Now, each 3 kilowatt hour battery pack is rated at 46.8 volts, but they connect in series, and then there's a DC to DC converter as well as a part of the battery management system in the cabinets, such that the terminal voltage at the cabinets is around 400. The 18 kilowatt hours of voltage from the batteries alone is at 281, but you saw how on the charge controller you could reduce a higher array voltage down to battery voltage. Well, that works the other way around as well. DC to DC inverters are every bit as good as and equivalent to a transformer that transforms AC from high voltage, low current to low voltage, high current. Do the same thing with DC with a DC to DC converter, and very efficiently these days. Battery round trip efficiency about 96.5% is what the manufacturer claims. So you know right away it's lithium. I think this is lithium, cobalt. I don't remember exactly. There's 6 different lithium technologies, and this is one of the favorites of for using in PV systems. Continuous battery power for one of these cabinets is 6.7 kilowatts. We were talking about that before, that you're limited to the amount of power you can draw out, not just the number of kilowatt hours, but the number of kilowatts. So this one, if you're powered up at 17.1 kilowatt hours, in other words, you got 6 of the packages in the blue case, then you can pump out 6.7 kilowatts. This particular system then obviously can do 13.4. And that will light up your stove pretty well, and it will run an air conditioner, and it's not a bad system for whole house backup with that kind of kilowatt hours. Multiply it out. 34 kilowatt hours a day for 30 days. That's over 1,000, isn't it? 34 times 30, 1,020. So if you use 1,020 kilowatt hours a month or less, this system will cover your whole house without having to turn anything off. And they're going in. People are buying them. They like that idea. Effectively, this is probably could be powering up almost 100% of the electrical needs of the structure. Backup mode, the inverter can kick out 8,000 watts, okay? Again, here's your motor start thing. The array, for a single inverter, you can have the array up to 15 kW. And that single inverter is, again, it's rated at, well, here's the ratings on it, 8 kW. And it has all the functions. Everything required by the National Electrical Code is right inside that inverter box. I don't even think I could type this out on a piece of paper and cram it into that small box, but it's an amazing piece of equipment. The biggest piece of equipment being the standby load panel. That's, I mean, I've been around for a while, folks. I'm 77 and first started doing these things in the year 2000. It's an amazing what's going on. And that's why I'm saying learn the basics, because by the time 2025 rolls around, these things will probably be history. Maybe it's all going to be in one box where you just connect two things to it. Who knows? Lots of control in here, lots of neat stuff, remote monitoring and stuff. Here's a question. Let's see what we got here. What's the manufacturer of the battery and inverter on the slide? This particular one is the Generac system. Generac. And that's not to say that I'm showing favoritism for Generac. My friends over at Urban Solar just happen to have a picture of this they were willing to share with me. Okay, let's see what we got next. Yeah, there's Urban Solar, local solar installer. They do an awful lot of residential work. Now here's a 120 240 volt AC coupled battery backup system. We've been doing DC coupled stuff. Let's take a look at an AC coupled schematic. And again, here's your inverter number one. That's the DC. That's the battery backup type inverter. You see the batteries are there and they connect directly to the inverter. No array, no charge controller, anything connected to that inverter. The array is connected to the other inverter, which is a straight grid connect inverter. So if that inverter, now let's look at some of the possible operating conditions for this. Let's say that it's daytime, the solar is running, the utility is up, it's just kind of like a normal day. So that means that the PUC is the point of utility connection. There's power flows in either direction from that point. Here's another question. Let's look at that right away. If the PV array is on a pool house about 120 feet from the house, what equipment goes into the pool house and what equipment goes into the main house? It partly depends on what's already in the pool house. We've had a couple of situations like this recently come up in our designs where they put a fair amount of PV on the roof of the garage. And so if your pool house roof is a nice south-facing unshaded roof, you might put some of the solar on the roof of that house. Depending on your connection to the utility, if you can backfeed a circuit breaker to tie into the utility, and actually, even if you don't have to do that, if you have to do a line side tap or some other way of getting to the utility, it turns out that actually you can put some of it on the pool house and some of it on the main house. And you may end up running a separate piece of conduit from the pool house to the main house. And when you do that, there are certain rules that you need a grounding electrode and a grounding electrode conductor probably at the pool house and at the main house, which will be part of the existing main. So depending exactly on your configuration, I've seen it done both ways. Seen one case where they put everything on the garage and ran the power over to the main house. And another case where they put some on the main house, some on the garage. These were using N-phase systems, incidentally. We'll talk more about N-phase system. Then we've got one coming up pretty soon. So that's kind of a general answer, but it is kind of a general question. But you simply need to follow the rules about live things near pools. Your 10 feet rules and 20 feet rules and whatever else is in the NEC 680 about swimming pools and power equipment. We did have, for example, a utility feed coming down with the utility meter on the wall of a house that was the swimming pools and us on that side. And we decided we are not going to mess with that meter. We're not going to try to get in there. We are going to put all of our equipment on another part of the house and feed the PV into the main panel. Actually, I think we fed it into, we put a separate junction box next to the main meter and rerouted the main meter feed through that junction box so we could tie in the solar there. So there are many ways to do this in terms of tying into the utility. They are all listed in National Electrical Code, Article 705.12. So you need to get to know that pretty well if you're into the business of designing systems and figuring out how to connect them in. Kind of a long question, answer to a short question, but I hope that almost does it. Let's see, I think this might work with microinverters taking place of inverter 2. Yes, the answer is true, but there is a particular trick involved with that, and I want to get to that. And that comes in taking a look at this system carefully and noting that we started out with the sun shining and the utility up. So therefore, the solar can make electricity. It's inverted, turned into AC, goes to the standby panel. If the standby panel has all it needs from the solar, it sends it back into the AC out terminals, which sends it up to the AC in terminal and back to the point of utility connection, which may be the main distribution panel. The loads in the panel take what they want of it. Anything left over goes back to utility. That's your normal time. Your batteries stay charged as needed because when the power is up, either solar or the utility, the inverter is capable of charging the batteries. Case number 2, utility is there, it's nighttime. Well, we're not making any solar electricity now, so that means utility has to provide all of the power to the main distribution panel. It's not shown on this slide, plus the standby panel. And that goes through L1 and L2 at the top, through that double pole switch up there, down to the AC out, and into the standby panel. And if the batteries need a little charge, the inverter will charge them until they're charged, and then it'll stop. That's case number 2. These cases, by the way, are listed, I think, on the next slide, but it's a whole lot easier to understand them if you're looking at the picture. Case number 3, no utility. In that case, that switch at the top there is going to open. That 2-pole switch at the AC in, that opens up because we have to disconnect from the utility, and that means any loads in the main distribution panel that might have been fed by solar previously are not going to be fed by it now. On the other hand, it's up to the solar to provide the energy for all of the needs of the loads in the standby panel. And it does that with the help of the batteries. So therefore, the solar comes on, makes AC electricity by way of inverter 2, powers the loads in the standby panel. Any leftover electricity goes to the inverter. And what can the inverter do with it? It can't send it out to the utility anymore. So the only option it has is to charge the batteries. Well, you know, you can only charge those batteries so far, and then they start getting unhappy. And what they do is their voltage goes up, and the inverter senses that the battery voltage is as high as it can go without damaging the batteries. So the inverter then has to talk to the other inverter and say, you got to slow down a little bit here, because we don't have anything to do with that extra electricity you're making. So you see that control wire at the bottom. Now that could be very well a wireless control, but it's nice to show it as a wire just to show that they have to talk to each other. And that's part of the point for any inverter when you've got two of them like this, and particularly when we're talking about end phase. So that's why we're getting to the answer to that question about does this work with end phase? The answer is yes. But the end phase microinverters have to be of the, what is it, this IQ7 and IQ8 series, so that they can communicate with other things that tell them they have to back off. Okay, because the end phase inverters would be in place of inverter 2 here on this particular picture. Okay, case number 4. So you see one of the cases is the battery is getting overcharged because there's nowhere for excess electricity to go if the utility is down. And so you can see this is where if your array is too big, you're going to waste a lot of electricity if the utility is down. So now the next thing is utility is down and it's nighttime. The only possible place we can get any electricity for those poor loads in the standby panel now is from the batteries. So that's when the inverter and the batteries get together and say, okay, let's go guys, it's time to make some electricity. And they make that AC and they power up those standby loads. And at 3 o'clock in the morning, the battery voltage has dropped to 48 volts, and the inverter notices that and said, oh boy, these guys are getting tired. And at a certain point, if those batteries go completely dead overnight, the only way that that inverter number 2 over there is going to wake up if the utility is down is if inverter number 1 has a way of telling it to wake up. Because see, if the utility is down, inverter number 1 has to be generating that voltage synchronizing signal that inverter number 2 is synchronized by, that turns it on. So therefore, inverter number 1 has to save enough charge in the battery so that it can wake up inverter number 2 in the morning. So that's all part of the control system as well. And that's what makes the AC coupled systems kind of interesting, because of the way the two inverters have to talk to each other. Now, this inverter in this AC coupled system, if we're looking at, say, a Powerwall system, this inverter and batteries, the inverter will be right inside the battery case, inside the Powerwall. And that Powerwall is then designed to have communication to talk to inverter number 2. Okay, so again, getting the general idea of how this thing works helps a whole lot in understanding what's out there today. So let's move on. And then this is what we just talked about, the 4 different operating modes. So you'll get this in your notes if you send off for the slides, and you'll see exactly, again, a reminder of what kind of control has to take place here in order for the system to function properly. Okay, so clicking my clicker the wrong way. Okay, limits and communication requirements. Okay, standby loads is determined by pass-through capacity of the battery backup inverters of the system. Okay, because you can have a lot of standby load as long as you got utility to feed them. But the National Electrical Code says that if there's no utility, then effectively your standby load system becomes a standalone system, and then the inverter does not have to be as big enough to power everything. It simply has to be big enough to power the largest load of the standby loads. So those are things you think about when you're doing the design if you want to get it right. Okay. Amount of AC sold back to the grid is limited by the battery backup inverters, because it's either a matter of how much they'll pass through from the other, or if the batteries are turning on and you're selling back to the grid from your batteries, That's another story. See, there's two different cases. You could be selling battery power back to the utility, and that's limited by that inverter. Or you can be using, uh, or you could be selling PV power back through an AC coupled system. Then your battery backup inverter simply has to have enough pass-through capability to pass through the entire output of the grid of the grid connected non-backup type inverter in that AC coupled system. Okay, so things to think about. Limit on available standby power during the day is determined by the battery capacity and the grid connected inverter to standby panel. And so here's your limits and stuff that are kind of useful to know about. All right. And so you'll have this if you get it. Here's your system design rules. Okay. And you may not be able to read it that fast, but again, if you're really interested, then order up the slides and you can sit down and have a look at them at your leisure. And there's reference material available as well that can be read to get even more background. Manufacturers have some pretty good stuff out. All right, here's our power wall. Does it look familiar? Power wall is an AC connected system. We've got this, you see the main meter. You've got a main disconnect with feed through lugs and interruptible loads up there because that automatic relay is part of the power wall system. And that automatic relay shuts down the connection between the utility and the rest of the world here if the utility goes down, because you're not allowed to dump power onto the utility when its voltage goes to zero. So then what happens? Those switch contacts open. You've got your main distribution panel with the main circuit breaker, and those loads become uninterruptible. So we have main disconnect with some interruptible loads on it. That would be a feed through panel up there on top. And then the bottom distribution panel may or may not have a main circuit breaker on it. And but that one contains interruptible loads. And more than likely, it's going to have a circuit breaker, but not always. It's pretty common down in my neighborhood for that main up on top to be a 150 amp breaker and a 200 amp panel, and the bottom one and the blue one to be a 200 amp panel, and no additional circuit breakers there. Your combiner panel there is important because that's where you bring your PV down, and that PV is now turned into AC by the PV inverter, which could be microinverters. Okay. And so therefore that we have an AC coupled system here now. So that means we have to have those same control constraints that we had in that last system. But not nearly as many boxes here, because that automatic relay, it is kind of in its own box in the combiner panel, but you can have additional circuit breakers in there and in addition. So it's conceivable your main distribution panel would simply be run out of the combiner. Here's your power wall down here, and you notice that there's a rectifier and an inverter in it because you charge it. Actually, you have a rectifier because you take AC in from the PV array or from the utility. Here's a question. We'll pick that up in just a second. And that charges the batteries in the power wall, and then the power wall has its own built-in inverter that sends AC back to the combiner panel. All right, let's see what we got here. A question. Only the newer IQ7, IQ8 will power with the power wall. I think so. I'm pretty sure you need to look at the power wall specs and the IQ7 and IQ8 specs. IQ7 and 8 were designed in order to match up with the IEEE 1547-2000. And I am pretty sure those are the only two that like to talk to the power wall. but don't take me as 100% on that, because I don't remember which ones we've been using. But it's easy to find out. You just go to your Powerwall specs. Okay, and I hope that's a good enough answer. I don't like to answer questions and pretend I'm a be-all, know-all, because I don't know it all. It's stuff new to learn every day. If the relay has disconnected the system from the grid, why do we care? We don't care, but the utility cares a whole lot. Because if the system is not disconnected from the grid, that means that the solar is going to keep on going, and it's going to be energizing the power lines, which have presumably become de-energized. And if you're a lineman working up trying to reconnect the 12,000 volt feeder that dropped because the pole blew down or something, and all of a sudden somebody's solar system is running, that 12 kV feeder is going to be hot, and you might be very unhappy if you're that lineman. So that's why IEEE 1547 came in. It's really UL 1741 is the test procedure for that. So that's where that came from. Another question, can you supplement with PV array with a small fossil fuel generator when the sun's not shining for several days? The answer is yes. See that combiner panel down there? That's where you put another circuit breaker, and you have to have simply a lockout such that the generator and the utility can never be on at the same time. The other thing is you need to be very careful that the generator and the PV is not on at the same time. Why would that be? Simply because if the PV is meeting all the needs of the loads, and it's excess PV with looking for a place to go, if the generator is connected, it will try to run the generator backwards, and the prime mover of the generator is not happy when a PV system tries to do that. So it's very important. I mean, we do a lot of systems that have generator plus PV, but the generator, the PV always has to be tied in on the line side of the generator so that it can be disconnected. The PV inverter power has to be disconnected from whatever the generator loads are being fed. Otherwise, it could be an unhappy day for the generator. Let's see, how is that configuration? Can I supplement PV with small plus? Oh, yeah, okay. I don't think I have a picture of that configuration, but you can look at, if you simply access the, well, the Generac people make generators. So just Google Generac battery backup solar system or PV system, and it will show you a number of different configurations that include using a fossil generator. Let's see, I'm going to click some of these here that we're done. Doesn't mean we're done, it just means I clicked the done button. If you didn't like the answer, you can always ask another question. Okay, let's see, time. 3:58, we have 2 minutes. Let's see how we can do here and finishing up. We're close. Okay, there's our Powerwall. And here's what Powerwall has. And we pretty much talked about this stuff, okay? System operation, we pretty much talked about this. AC coupled system, same story. And here's that Powerwall system you saw on the very first slide. Now the covers are on. You can see that's the gateway in that box on the left, standby load panel, combiner panel. The PV is coming in from the wall from another place. And a couple of Tesla Powerwalls rated at about 13.5 kilowatt hours each. So we're looking at 27 kilowatt hours of storage here. Scalability. Generally, you can scale these things up. You got, say, an 8 kW inverter, 8 kW system. You can oftentimes use about 10 of them in parallel. Get yourself up to 80 kW. Need to be a little careful. Sometimes the battery systems have to, each inverter may need to have its own battery system. Okay, so you need to check the manufacturer's specs. Watch out with the battery connections. And make sure battery charging rates or discharge rates don't exceed the manufacturer's limits. It's easy to do that if you're not careful, have too much array. Then you might have way too much current for charging the batteries, and that can shorten their lifetime. So, and another thing you watch for with the scalability of the systems. And inverter output currents are limited, so the maximum output power determines the load calculation at the point of utility connection, and that is National Electrical Code 705.11 or 705.12. Okay, a couple of code references there. What's coming next? More communication, more control. The whole idea the utility can ask your power wall to please sell it some electricity at 3 o'clock in the afternoon. It's coming, and the power walls are ready for that. Much more sophisticated utility bidirectional interaction. We got cell phones, we can do anything. Why not that? Integration with other sources and systems. A lot of fancy stuff. I don't know, sun, moon, planets, stars, maybe they're next. Well, we've been to most of them. So then what? Anyway, I'm an old guy and I still intend to be a part of it because this is exciting stuff. And I thank all of you for joining. I'm just going to click here. You can see this is the end, but there are a bunch of additional slides here that do other things, as you can see. So in any case, I'm going to check to see we got some Q&As. Let's do those. What do the abbreviations JB, N, and OCP stands for? Oh, okay, good question. JB is junction box, that's all. It's where you splice some wires. N stands for neutral, and that's the grounded conductor of a system, and OCP is just overcurrent protection, fuses or circuit breakers. And Ernest, you're welcome for the presentation. I've enjoyed it. I hope you have. And I'm going to stay here a while and see if we get any more Q's and A's. But meanwhile, the session's over, and I hope you've all gotten something worth spending that 2 hours this afternoon. Appreciate your ratings, comments. We try to improve on things based on what we hear. Copy the slides. Just follow the instructions. I think if you go to the chat box now, you'll see the instructions for doing that. Let's see, and you'll see what's in chat just to make sure. Yeah, here's the messages in the chat box will give you information of basically going to the PDH website. Oh, a couple more. Let's see. Okay, ladies and gentlemen, I didn't get to see your names. Wish I could have, but I guess I should have clicked on the participant list. Maybe I can click here quickly while we got Eric and Ernest and Harold and James and Jeffrey and Joe, John, Kathy, Keith, Micah, Michael, Randall, Robert, Steve, Walter, Winslow. Okay, well, thanks to all of you for joining our group this afternoon.